Okay guys, in previous lesson we have read the R models for the true models in here, and also we need to add the what noise sigma 50 and round n dot noise sigma and W noise is created in here. So how we can apply the time parameters to identify the R system? Identification process is started in here. First of all, apply a low pass filter. Okay, so the cutoff frequency is 2. For example, the alpha is derived from the what to 2 times pi times fc times ts. Okay, and so a lp is equals to the what, the 1 minus 1 minus alpha. Okay, this is the coefficients, and b lp low pass filter parameter is equals to what, the alpha. Okay, so the v filtered is obtained with the what, the filter parameters b lp a lp. Okay, this is the what this is the R system response, alpha divided by s minus 1 minus alpha. Okay, and also we need to provide the V noisy signals in here. Okay, so this is the R filtered signal. Okay, and so estimate steady state values from the what, this signal, and ss is the round value of the n times 9.0. Okay, and wss is equals to the what, the mean W filtered and SS and. Okay, so the settling percentage is assigned with the 0.05, and V upper must be defined with the WSS times 1 plus settling percentage, and W lower is equals to the what, the WSS times 1 minus settling percentage. So how we can find the index where the response first enter the what, 5% error, the lower or upper? We can use the index ts variable in here. The find is a function defined in the Matlab. W filtered signal greater than equal to the W lower, and W filtered smaller than equal to the what, W upper 1 and first. Okay, this returns to the what, the first point of the what, the 5% error rate with the what between the WSS values and the R response. Okay, so also we need to confirm that it stays within this band and look ahead to ensure it remains within band. Okay, the remaining within band is assigned the all W filtered index ts, this is the first point, and up to end is greater than equal to the W lower and W filtered index ts and is smaller than equal to the W upper. Okay, so if I check this system, if remaining within band and ts is equals to the what, the t index ts. Okay, This is the settling time, else ts should be equalized to the none, and warning, system does not settle within the simulation time. Okay, these are the conditions. Okay, and so if I run this code, and then we will have the TS at what, 0.42 seconds. Okay, and so we will find it. Otherwise, we need to give the warning, just like this one. And if we found to what, to this settling time, time constant is calculated with what, the tau s is equals to what, the TS and divided by 3. Okay, these are formulations, and so the A ist value minus 1 tau est. Okay, and B ist value is equalized with the what, the minus A est times WSS divided by U0. Divided by U0. Okay, these are conditions. C, the U0 PWM rate is assigned and BS is found. And after that, J assumed is assigned 0.1, and C est is equals to what, minus A est times J assumed, and KV est is equals to what, the B est times J assumed. Okay, so after that we need to print the whole values in here, just like this one, the estimated parameters using time response. Okay, so the fprintf is equals to what, the C est is equals to the 4% dot 4 new line C est and also C true must be assigned in here C true, and also KV est and KV true is assigned, KV true, KV est, and estimated settling time is equals to the what, TS, and estimated steady state value is equals to the what, WSS. Okay, so if I run this code, and then we will have the C estimated value is 0.71, KV estimated value 11.69, and the other one is these terms. Okay, these are the conditions for the what, for our model. Okay, if I choose to what, to this tau est value is 4, and so this 4 is closing to each other in here for the what, for the 5% values, because we have the settling error or the noise sigma values in here, just like this one, this closing to each other. But if I choose the decreasing the level of these terms, and so this is closing. Okay, and also we can assign these values, and so we have the sum parameters in here, just like this one. And so for TS is equals to the what, TS 4 divided by tau s in the what, in our conditions. Okay, so how we can estimate or simulate this response, simulate the model. Okay, so we est needs to be built with the zeros and 1, and A est CT is equals to the A est and B est CT continuous values, B est should be given, and for K is equals to the 1 to minus 1, And first of all, the compute continues, and v dot est is equals to the what? The e est ct times w est k plus b est ct times uk. Okay, and after that we need to use the forward Euler equation. V est k plus 1 is equals to the w est k plus ts times v dot est. Okay, and so how we can plot to these values, the figure, the plot. First of all, t, w noisy signals, b, and line white is equals to the 1. This is the noisy signals, okay, and the hold on w filtered. Okay, this is can be equal to the green 1.5, and also we need to plot to the what? Two estimated values. This can be r dot dot, and so this is assigned to the two values. Okay, and after that the x label time sec, y label angular velocity. Okay, and the legend must be assigned first of all the measured response. Okay, the second one the filtered response, the third one estimated response, and after that grid on should be applied. And so if I run this code, and then we will have three dynamics in here just like this one, and so the filtered response is here. Just see that this is unnoisy signal. Estimated response is on the curve of what? The measured response. That's good response to what? To model of these terms. And so we closing to what? The main values of these terms, just like this one, because the RCS and KVS is closing to the true values in here. But if I put or increase the noise signal values up to what? 50. So see that in the 50 we cannot have the CS value because the warning system does not settle within the simulation time, which means that this condition is written on this one. We cannot determine what the TS value or the settling time because we have too many noise in here. And so in the first place we need to what? We need to, for example, either this FC must be reselected in here, just like this one. See, 0 CS is coming from in here, C true is 1, KV and K true are closing, but not so close that before to the what? To the other terms. Okay, this is so important to the what? To the model the R system based on this information. But in the real life you cannot have this kind of noises, and so we can proceed with what? With the 30 values in here, just like this one. But in the 30 values we too much apply the discrete low pass filter in here, and so the R filter signal does not match the real one, and so we need to increase the cutoff frequencies in here, and so the cutoff frequencies creates to the what? To this response, and so we can close R true response, or we can increase also FC to 3, and then this signal is to what? Is closing to each other, and so you need to optimize the R steady state response and the time response based on the what? Your noisy signals, and so you must apply perfect filter to what? To take the model parameters in the what? In the true domain. Okay guys, that's all for the what? For the time parameter estimation for the what? For the first order signals. And so in the next lesson we will talk about the how we can determine the or estimate the parameters of the second order system on the what? The mass spring damper systems. Okay.